The PAK-DA project emerged from a long internal debate within Russia's aerospace and defense establishment about what kind of strategic bomber would be viable in the middle of the 21st century. As early as the late 1990s, Russian engineers and military planners recognized that the traditional formulas for bomber design, speed, altitude, and sheer missile carrying capacity, were becoming less effective against modern air defense systems. Radar networks were expanding in coverage, computing power behind signal processing was growing dramatically, and new types of sensors were becoming widespread. A high-speed bomber could still be detected by long-range radars. A large non-stealth bomber might deliver powerful weapons but would need to fire them from far outside defended space, and any platform with exposed engines, protruding surfaces, or angular features would inevitably show up on multiple types of detection equipment. Against this backdrop, the idea of a new bomber could only be justified if it avoided these weaknesses from the start. This is why the PAK-DA concept took shape around a flying wing configuration. Such a layout spreads the mass of the aircraft across a broad, continuous surface, eliminating conventional fuselage and tail assemblies. By doing so, it reduces the number of edges and angles that produce radar reflections. This design also provides a large internal volume to house the fuel, equipment, and weapons required of a strategic bomber while minimizing external protrusions. Engineers examining this approach were influenced by global trends in stealth aircraft development. A flying wing also allows more efficient aerodynamics at subsonic speeds, enabling long endurance without demanding engines that produce excessive heat signatures or require large external nacelles. From the military's perspective, this configuration fit their requirement for long-term relevance. Even as air defenses evolve, a stealthy flying wing has a better chance of remaining survivable than a traditionally shaped bomber, which would inevitably show up more strongly on radar. As Russia moved from concept studies to actual planning, the program had to account for the realities of funding, industrial capacity, and competing priorities. After the collapse of the Soviet Union, Russia's aerospace sector went through a period of contraction. Many projects were cancelled, and existing aircraft were used longer than originally intended. When the strategic bomber modernization discussion resumed in the 2000s, the focus was initially on upgrading existing platforms, the Tu-95 and the Tu-160, because they were already in service and their modernization could begin immediately. Meanwhile, the concept of a brand new stealth bomber remained on paper. Only after the economy stabilized somewhat, and after lessons from modern warfare emphasized the necessity of long-range precision and low observability, did the program receive sustained attention. The designers had to solve several problems at once. One was materials. An aircraft intended to evade radar requires careful selection of structural composites, coatings, and surface treatments. Russia has developed composites for various aircraft programs, but creating large, load-bearing composite sections for an all-wing design demanded additional effort. Another challenge was integrating the engines in a way that shields the compressor face, one of the brightest radar reflective surfaces on any jet, from detection. This can require serpentine ducts, special coatings, and carefully shaped intake geometries. Engineers also had to consider thermal management, because a strategic bomber flying long missions generates considerable heat even at low speed. The overall goal is to smooth out physical and thermal signatures so that the aircraft presents only faint, non-distinct returns on modern sensing equipment. The internal layout of the aircraft needed to accommodate several mission profiles. A strategic bomber does not operate like a fighter that accelerates and maneuvers aggressively. It typically cruises at efficient speeds for many hours, sometimes crossing continents or oceans before releasing its weapons. This means the cockpit and crew systems must support long-duration missions with high levels of automation and reliable environmental controls. The bomber also requires redundant navigation and communication systems capable of operating in an environment where an opponent may attempt to jam or spoof signals. Because the aircraft will carry nuclear weapons as part of its mission set, strict security and safety standards apply to the control systems and weapon interfaces. Integration of weapons is one of the core design drivers. Russia relies heavily on long-range cruise missiles for strategic missions, and these missiles vary in size. The new bomber therefore needs bays deep and wide enough to house several of these weapons internally. By keeping them inside the fuselage, the aircraft maintains its low profile on radar. Designers must also ensure that the weapons can be released cleanly without creating airflow disturbances that compromise stability. Over the long service life expected of such a bomber, new weapons will emerge, perhaps faster missiles, perhaps more advanced guidance systems, which is why internal mounts and wiring architectures are often planned with flexibility in mind. During the years when the project moved from design studies to physical construction, Russia's aerospace industry had to re-establish certain manufacturing capabilities. Producing a stealth aircraft is not just about the design itself but about the precision of the fabrication process. Panel alignment must be extremely accurate. Surface treatments must be applied consistently. Even small gaps or bumps can increase radar reflections. Establishing this kind of manufacturing discipline takes time, and it is likely that part of the extended development timeline resulted from the need to refine these production methods. Prototype construction also typically reveals issues that cannot be foreseen during computer modeling. These issues must be resolved before flight testing begins. The development of the engines is another area that required attention. Strategic bombers need engines that balance fuel efficiency, durability, and stealth considerations. They are not optimized for the highest possible speed but for long, stable operation at cruising velocity. Engine design affects not only performance but also thermal and acoustic signatures. To reduce detectability, the bomber might use specialized exhaust nozzles, shielding, or cooling techniques. These developments sometimes progress more slowly than structural fabrication because engines must endure rigorous testing before they can be trusted in a strategic role. While engineers were working on hardware, military planners were determining how the aircraft would fit into future operational concepts. Modern bombers are not lone attackers, they function as part of a broader architecture that includes satellite positioning, long-range communications, airborne sensor platforms, and ground stations capable of updating target coordinates during a mission. Because of this, the PAK needed to have data links and onboard computing systems capable of handling these networked operations. Russian statements over time have suggested that the platform will support real-time mission adaptation, meaning the crew can receive new targeting information en route and adjust their plan accordingly. This is particularly important in long-range operations where the situation on the ground may have changed significantly by the time the bomber arrives near its launch point. Another factor in the program's evolution was the need to balance innovation with reliability. Strategic bombers must be dependable and maintainable for decades. For that reason, completely experimental technologies are often avoided in favor of proven systems adapted for stealth operation. The aircraft must be large enough to carry significant fuel and weapons but simple enough to maintain without excessively specialized equipment. Russia's experience with other long-term aircraft, like the Tu-95, likely reinforced the value of maintainability and robustness even in a cutting-edge platform. The timeline for bringing the aircraft to flight readiness has stretched as the program encountered the typical complexities of modern aircraft development. Some delays stem from the need to test and certify components individually before they can be installed on the prototype. Structural test articles must undergo stress testing, which can reveal design aspects that need adjustment. Systems such as landing gear, fuel pumps, electronics, hydraulic actuators, and environmental controls are tested for thousands of simulated hours. Only after everything has been checked and refined can the first full prototype be prepared for flight. Even then, the initial flight is only the beginning of a long phase of testing that can include hundreds of flights spread over several years. Once a prototype finally flies, engineers will evaluate stability, control authority, aerodynamic performance, sensor reliability, and stealth characteristics. Stealth testing requires assessments from multiple angles and distances, often using specialized measuring equipment. It is common for stealth aircraft to undergo modifications to surface coatings, panel alignment, and internal systems after initial flight tests, as real-world behavior often differs from predictions. When the aircraft eventually enters service, it will likely do so gradually, with a small number of early production models undergoing operational evaluation. Crews will train on new procedures, maintenance teams will learn the specifics of the airframe, and strategies will be refined to integrate the bomber into Russia's strategic deterrence structure. Over time, the bomber will supplement and partially replace older aircraft, but the transition is expected to span many years, if not decades, given the large scale and long lifespan of strategic aviation programs. In a broader context, the PAK-DA symbolizes Russia's intent to maintain long-range strike capability into a future where stealth and precision form the backbone of strategic operations. The aircraft aims to ensure the ability to deliver weapons from great distances, remain undetected until mission completion, and integrate with evolving command and control systems. The design philosophy reflects both long-term military planning and the recognition that high-end air defense environments require aircraft that minimize observability in all detectable signatures: radar, thermal, acoustic, and electronic. As it continues through development, the PAK-DA will represent one of the most complex aerospace projects undertaken by Russia in the post-Soviet era, involving a fusion of aerodynamics, materials science, propulsion, electronic warfare, and strategic doctrine into a single long-range platform intended to remain viable for multiple decades.